So it's great honor to have a speaker, Paul Seymour from Princeton University. So he will talk about the Erdős-Hajnal conjecture is true for excluding five cycles. Yeah, Paul, please.
Okay, thank you. Can you hear me? Everything
Yes.
works? So I want to talk about a new result, or several new results, about the Erdős-Hajnal conjecture, but I thought I would start with a survey of what was already known about the conjecture, and then I'll go on to the new results. This is joint work with Maria Chudnovsky, Alex Scott, and Sophie Sperkel. So this is a problem about induced subgraphs. So an induced, I don't know how much I should assume that you know, but an induced subgraph is a subgraph you can get by deleting vertices. You're not allowed to delete edges just by themselves. If you want to delete an edge, you must delete one of its endpoints. So you take a subset of the vertices and you have to keep all edges within that subset. And let's say a graph is H-free if it doesn't contain a subgraph, an induced subgraph isomorphic to H. And I use alpha for the size of the largest stable set and omega for the size of the largest. And the question is, how large? What's the maximum of alpha and omega, of the stability number and the clique number? Can you say it must be large? Well, for general graphs, you can say it's log n. It's constant times log n, and that's the truth. You can make graphs where the largest clique and the largest stable set are only log n. Graphs with n vertices with the largest clique only that big. But as soon as you exclude something, you can do better. As soon as you exclude a graph, any graph, then you get largest clique or largest stable set is at least 2 to the square root log n, 2 to the constant times square root log n, which is much bigger than just log n. But if you look at specific graphs where we know the answer, so you can do even better. So for instance, with P4 free graphs, the largest clique or stable set is number of vertices to the half. For the K2 free graph, the number of vertices is G to the 1 over T minus 1. For bull free graphs, you know what the bull is? You take a 4-vertex path and you add another vertex joined to the middle 2 vertices. For bull free graphs, there's a clique or stable set of size G to the quarter. For C4 free graphs, there's a clique or stable set of size G to the third. And that's the conjecture, that you can always get some polynomial. If you call this a polynomial, G to the constant. When I was brought up, a polynomial meant G to an integer constant. But anyway, we're going to call G to the third a polynomial in G. And the conjecture is, for every graph, there is a constant C, such that for every H-free graph, it's got a large stable set, a large clique or stable set of size at least order of G to the C. And it's famous conjecture from 1977. It's been worked on a lot. And there's not an awful, we haven't made a lot of progress with it. I thought it was false, but I'll tell you about that later. Let's say a graph has the Erdős-Hajnal property if there is such a constant. If there is a constant so that max of alpha and omega is at least G to the C for every H-free graph G. By the way, I wanted to say, if you have questions, please interrupt. I want to do this clearly enough that you can follow the proof and understand what I'm saying. So if you don't understand, please stop me. It probably means that other people don't understand either. So do interrupt if you want to. And to interrupt, just talk. Don't bother with the chat. Just talk. So what do we know about the Erdős-Hajnal conjecture? Which graphs do we know it for? There's a theorem of Allenbach-Solomoshi from 2001 that says if you take two graphs and you substitute one for a vertex of another, then the bigger graph you've just made has the Erdős-Hajnal property. What do I mean substitute? You take a graph H1, which has the property. So excluding that gives you a clique or stable set of size n to the C for some choice of C. And here's an H2, excluding that gives you a clique stable set of size n to the C for some other choice of C. And now you pick a vertex of H2 and you replace that vertex by H1, meaning you do this, you replace the vertex by the set and you make all these vertices adjacent to what used to be the neighbors of this one vertex V. And that's basically what's known. So any graph you can build this way by substitution has the property, but which graphs can you not build by substitution that have the property, the building blocks? And there's very few. There's P4, there's K2, and those are all the graphs that are indecomposable with at most 4 vertices. So it's known for all graphs with at most 4 vertices. But the only other indecomposable graph for which it's known was the bull. And so that was the complete list of everything it was known for: the bull and P4 and K2 and I guess the complement of K2 and everything you could make from that by substituting graphs for vertices of other graphs. So today I'm pushing the list a little bit further. It's convenient to talk about kappa, which is the product of alpha and omega. And if I want to say the max of alpha and omega is big, it's just the same to say kappa is big. I mean, if kappa is big, then one of alpha and omega is big. And if one of alpha and omega is big, then the product is big because they're both at least 1. So a graph has the Erdős-Hajnal property if and only if there's a C such that kappa of G is at least G to the C. It's a different C. If I take the C that works for max of alpha omega, then here I have to take 2C or something. Well, in one direction I have to take 2C, and in the other direction I have to take C. But it's an equivalent statement. There's a C with this property if and only if there's a C with the property I said before. And this is just more convenient. And in general, for a set of graphs, we'll say a graph G is H free if G doesn't contain any induced subgraph in the set H. And similarly, we'll say a set of graphs has the Erdős-Hajnal property if there's a C such that kappa is at least G to the C for every script H free graph. Is everything clear so far? Everybody happy? Please, as I said, please interrupt if you don't understand.
Yes, it's fine to me. Yeah.
I'm sorry, it's fine?
It's fine, yes.
Okay. So what do we know? If you define G to be the G bar to be the complement graph, it was, as I say, it's known for all graphs with at most 4 vertices. On 5 vertices, there are some graphs which is not known for. For instance, P5, the 5-vertex path, and that's open. And in fact, it's still open, despite what I'm talking about today. Though you would think that our result today would settle this, but it doesn't. At least I don't think it does. By the way, showing that a graph has the Erdős-Hajnal property is the same as showing that its complement does. Because if a graph if G doesn't contain H, then the complement of G doesn't contain the complement of H, and the product of alpha and omega is the same for G and G complement. So the graphs that have the Erdős-Hajnal property come in complementary pairs. It's easy to see if you exclude P5 and P5 complement, then you do have the Erdős-Hajnal property, or rather this set has the Erdős-Hajnal property. And Maria and I extended that, seems like a long time ago now, it was only 5 years ago, that if you exclude P6 and P6 complement, you get the Erdős-Hajnal property. And if P7, P5 complement have the Erdős-Hajnal, has the Erdős-Hajnal property. And we thought that was good. We worked hard for that. And it was dwarfed by a theorem of Bousquet, Lagut, Thomaset that said take any path. You could exclude it and its complement and you get the Erdős-Hajnal property. So, and this was a really nice proof. Much more beautiful than our old proof, and really nice proof. You should, if you can, you should read that paper. It's very pretty. And this has been extended further, that if you take a subdivided caterpillar, so a caterpillar is a path and you attach leaves to the vertices, any number of leaves to the vertices. And a subdivided caterpillar means you can subdivide these legs. You can replace the leaf edges, the legs by paths instead of just edges. So if you exclude a subdivided caterpillar and its complement, you get the Erdős-Hajnal property. And that was extended further, that actually if you exclude any forest and its complement, you get the Erdős-Hajnal property. So we've gone a long way up from this old theorem, which already, as I said, was quite hard, but this is much more general. And today I'm going to give you a result that extends this further. But these are all results about excluding pairs of graphs. For excluding a single graph, we still don't know any more than we did, except we're going to claim it's true. We're going to show it's true for C5. That's the new result, the sort of most significant new result, that C5 has the Erdős-Hajnal property. Let me tell you some more of the new results that come out by the same method. If you add a hat to C5, which means you take C5 and you add another vertex with two neighbors in C5 adjacent, then that graph and its complement, the set of these two graphs has the property. And C6, C6 complement and C7, C7 complement have the property. More generally, this graph has the property. If you exclude this and exclude this and its complement, that has the property. Which contains all those other results, because I mean, if you believe this fact about that graph, and you really just care about excluding C5, well, take a graph with no C5, then it certainly doesn't contain this, because this contains C5 just here. So if you know that excluding this gives you a polynomial sized clique stable set, then certainly excluding C5 gives you a polynomial sized clique stable set. And the same for C6, because there's a C6 here, and the same for C7, because there's a C7 there. So these two results follow from that result. And other things we can get is, if you exclude any cycle in any, for any cycle and for any forest, if you exclude the cycle and you exclude the complement of the forest, you get the Erdős-Hajnal property. And there are more general results. Let me tell you what a star expansion is. So a star expansion of a graph is you take the graph. In this case, I've drawn P5, but it can be any graph. You take your graph, you add a leaf to every vertex, and you add another vertex joined to all the new leaves. This side is a star expansion of the house, which is the complement of P5. What I had on the previous slide that's the star expansion of P4. Here's the theorem that for any forest, this set of 4 graphs has the Erdős-Hajnal property. But what's that? That's the star expansion of the forest. That's the star expansion of the complement of the forest. And that's the complement of these two graphs. So for instance, these two graphs plus their complements, that set of 4 graphs has the Erdős-Hajnal property. And they're full of C5s. You know, if all you really wanted was C5, then we've got plenty of C5s in this theorem. Another result, that if you exclude a forest, if H1 is a forest and H2 is a star expansion of a forest, possibly a different forest, then if you exclude the complement of H1 and you exclude H2, you get the Erdős-Hajnal property. I probably won't have time to talk about the proof of this, but I might. We'll see. These are more or less, all these results are consequences of the same lemma. And I want to prove the lemma in detail. And then if there's time afterwards, I'll show you how to derive these consequences. But I want to do the proof carefully, or moderately carefully anyway. Some terminology. We'll say, if I have 2 disjoint subsets, I'll say they're complete if every vertex in the first is joined to every vertex of the second. And anti-complete if there's no edges between them. And it's a pure pair if it's either complete or anti-complete. A good theorem we proved, when did we prove it? Maybe 2 years ago, but it was published this year, is that for every forest, there's a constant. So that if you don't contain the forest and you don't contain the complement of a forest, you have to have a linear sized pure pair. So this is not about Erdős-Hajnal. This is about having big pure pairs. In a general graph, you don't get big pure pairs. The best you can get is log n versus log n. But if you exclude a forest and you exclude the complement of a forest, then you get a linear size pure pair, both sets linear. Let me show you, this does imply that that H and H complement has the Erdős-Hajnal property. It's just a consequence of this fact. Because let's see that, just because this is a kind of calculation we'll need to do again. So you choose, I'm going to change that C to be an epsilon. This C should be an epsilon, and that I changed the wrong C. I changed this epsilon to be a C. I'd confused myself now. Wait a minute. So this is epsilon. Choose epsilon as above. That's right. Choose C satisfying this. Now let's prove that cap of G is at least G to the C for every H and H bar free graph G. We'll do it by induction. So from this theorem, we know there's a linear pure pair, both of size at least epsilon times G. By induction, I can look at kappa. I'm going to write kappa of A, meaning the kappa of the subgraph induced on A. Kappa of A is at least A to the C, which is at least epsilon G to the C. And similarly, kappa B is at least that. So what's kappa of the whole graph? It's at least the sum. Kappa of G is at least kappa A plus kappa of B, which is twice this, which is G to the C, because the way we chose epsilon. By the way, why were we able to choose C like this? This too is important. If I just wanted to say epsilon to the C is at least 1, I can't, because epsilon's less than 1. I don't care what positive power you raise it to, it's still less than 1. Somebody's scribbling on my picture. Who did that? Somebody just scribbled in green all over the slide. What's happening?
Yeah, I don't know. Yeah, maybe.
Let's hope that doesn't continue. So if you believe this is true, what's this step? The kappa of G is at least kappa of A plus kappa of B. Let's see why that's true. I've still got these green scribbles all over the screen. Oh, that's stopped now. That's better. Thank you. Whoever did that.
Yeah.
No, it's coming back.
Yeah, sorry.
Does anybody know what that is?
Yeah, just don't write there, because I just myself I removed them. But
okay, I didn't think it was possible. Anyway, okay. So why is this true? That if you have a pure pair, then kappa of the whole graph is at least kappa of A plus kappa of B. Well, you could take complements. I mean, if I have a pure pair, I can assume it's an anti-complete pair, because if it's a complete pair, then just go to the complement graph, nothing changes. So then kappa of A plus kappa B is this by definition, it's alpha times omega. And omega times A is at most omega times G. And same here, that's at most omega times G. So we can just take out the common factor. And alpha A plus alpha B is at most alpha G, because there's no edges between A and B. I can take the biggest stable set of A and the biggest stable set of B and just take their union. It's still a stable set. So this is true, which is kappa G. So that's why that's the case. Similarly, let's say a pure party is lots of sets instead of just a pure pair. Pure party is lots of sets, but they're all pairwise anti-complete or all pairwise complete. And if you have a pure party, then again, kappa of G is at least the sum of the individual kappas. Same proof. What are we going to try and prove? We're going to try and prove if you don't, for instance, if you don't contain C5, then there's a kappa of G is at least G to the C. If you don't contain C5, and I choose C sufficiently small, so let me say it backwards. If I choose C sufficiently small, then for every graph G that doesn't contain C5, kappa of G is at least size of G to the C. So we're going to try and prove that by induction on the size of G. In other words, so therefore we can assume that kappa of G is less than G to the C, but it's greater than or equal to for every induced subgraph. For every induced subgraph different from G. Kappa of G prime is at least G prime to the C for every induced subgraph of G. And if you have that property, let's say the graph is C critical. And another way to say the Erdős-Hajnal conjecture is that for every graph G, if C is sufficiently small, then you can't have an H-free graph that's C critical. For every graph H, if C is sufficiently small, then there is no H-free graph that is C critical. That's the same as the Erdős-Hajnal conjecture. So we're going to be looking at C critical graphs and trying to prove they must contain H if C is sufficiently small. They must contain C5 in our case, when C is sufficiently small. Is that clear? We're going to prove a lot of things about C critical graphs, so this is a good definition to understand. This is a lemma we'll also use several times, so let me give it a name. I'll call it the party lemma. That if you have a C critical graph, you can't have a pure party of T sets, each of this size, each of its size at least this. And the reason is, suppose you do, I have T sets, all of big size, then kappa of the whole graph is at least kappa of all these sets added together. And each set is at least its size to the C. And its size to the C is T to the minus 1 over C. So is this thing raised to the power C, which is 1 over T times G to the C. And I'm adding T of them together. So I just get G to the C, which is what we wanted to prove. So you can't have a pure party of T sets because then kappa of the whole graph will be too big. It wouldn't be C critical after all. A rake, a TK rake. A rake is a subgraph that looks like this, and it's got two important numbers. One is the number of these things, which is T, and one is the size of the red sets, which is K. And what I mean, I'm going to be looking for a subgraph like this in my graph G, and it's nearly induced. It's induced, except there might be edges between the red sets, and there certainly can be edges inside the red sets, but there might be edges here. But there are no edges like this, for instance. There's no edges here. There's no edges here. There's no edges from this vertex down to the bottom. And so the red scribbles are back. Thank you. Does everybody else see those red scribbles when I do?
Yeah, yes, we saw that. Yeah.
Oh, good. I thought I might have been having hallucinations or something. So a rake is a subgraph like this. And here's the rake lemma. It says that for any graph H, and for any number you want to specify, there is a gamma, such that if you choose C sufficiently small, then something nice happens. So if I take an H-free graph that's C critical, then either G or G complement has a big rake. A rake like this with T sets of size gamma G over T squared for some T at least T0. You can't say, I don't know how to say, give you a bound on T. All I can say is T is at least T0, but it might be huge. T is not a constant. T could be polynomial in the size of the graph. But it is true that if you take a critical graph, then it has a rake with these parameters for some value of T. If you take a C critical graph and it's H-free, then either G or G complement contains a rake like this for some value of T, at least T0. And that everything else follows from that. So I'm going to spend most of this lecture proving the rake lemma, and then we'll have a few minutes at the end deriving things from the rake lemma. So let's see, first of all, that you get C5. If you believe the party lemma and you believe the rake lemma, well, you should believe the party lemma because I proved it. if you believe the rake lemma, then let's get the C5 theorem. So take H to be C5 and take T0 to be 2. And then this thing tells me there is a value of gamma that satisfies the rest of the rake lemma. So choose that value of gamma. And I'll choose C really satisfying this lemma, which all sufficiently small C do satisfy. So have this property. And make sure that C is small enough that this quantity is at least 1, which you can if C is really, if C is really small, then this exponent is really big. So I can make this quantity bigger than 1, even if gamma is very small, because gamma is a constant. I get to choose C after choosing gamma. So I can make this bigger than 1. And now suppose that H is C5 free and C critical. And we need to prove that there's no such graph. In order to prove Erdős-Hajnal for C5, we need to prove that, and to prove that this value of C works, then I need to prove that you can't have a C critical graph that's C5 free. So suppose you have. The complement is also C5 free and C critical, and we can replace the graph by its complement. So let's do that if we have to. So we can assume that, we know here that one of G and G complement contains the rake, but we can assume it's G. So G contains this rake now. Now, there's no edge, but if you had an edge between two of the red sets, that gives you a C5. All the rest of this is induced, right? You take these 3 vertices in your edge here, and that's C5. So there's no edge between the red sets. And that means they make a pure party. But they've got size gamma G over T squared. And now you do the calculation. T, what's this? I've forgotten what this is about. That's the way I chose gamma. I chose gamma at least this. So this is at least that, which is this. Oh, the T is at least 2 because I chose T to be at least T0. So, and this exponent is negative. So if I replace this 2 by a bigger number, the thing gets smaller. And so that quantity is at least this quantity. And that's cancel the T squared, you get T to the 1 minus 1 over C times G. And you can't have a pure party with T sets all of that size. That's what the party lemma says. So that's the proof for C5, if you believe the rake lemma. Right? Any questions so far? All right, so to prove the rake lemma, let's start by getting this bit of it. To be a rake, there's supposed to be another vertex on top adjacent to all these A's, but we won't bother with that at the moment. And I'm not going to bother. I don't want to think about the edges between the A's either. All I want to do is get a bunch of stars like this where there's no diagonal edges. So it's really a question about a bipartite graph. So let's start with a bipartite graph. And I want to say there's a big rake in some sense. So what do I need? Well, first of all, I need B is big. I want to choose, I'm sorry, I'm not trying to get a rake, I'm trying to get a comb. Let me go back to there. This is a comb. It's a rake minus the handle, minus the vertex joining everything together. So we're trying to get a big comb. So suppose I tell you B is big, but I also tell you every vertex in A only has a few neighbors in B. Then we'd like to find a comb with A1, with the vertices A1 to AT up in A and all the subsets B1 to BT down in B. What can we get? Well, nothing so far, because I better say, there might be vertices in B with no neighbors in A. So if just telling me that B is big doesn't tell me anything, because there might be a whole lot of vertices here with no neighbors in A and all the rest is small. So let's assume everybody in B has a neighbor in A. Now this question makes more sense. And what we'll prove is this theorem, that if I have a graph of the bipartition and you tell me 2 numbers, gamma and delta, And we know that the size of B is at least 19 times gamma delta to the half. And you tell me every vertex in B has a neighbor in A. And you tell me every vertex in A has at most delta neighbors in B. Then you can get a comb of this size with these parameters. T sets of each of size at least gamma over T squared. I don't know what T is. It's at least one, but it might be one. But there's, so that's, do you understand the statement? I keep saying the size of the comb, but that's not really what I mean. It's a comb. If T is small, the sets are big. If T gets bigger, the sets get smaller. But for some choice of T, you can get a comb with these parameters, is the claim. Is it clear?
Yes.
So, all right, here's the proof.
So when you say you have a comb, you mean you get it as a kind of induced subgraph, but not exactly induced, right? Because
Well, I'm assuming we're in a bipartite graph now.
oh, I see.
I'm just working in a bipartite graph between A and B. And I want to get a comb with the AI vertices in A and the B's in B. And it is supposed to be induced now. I want the, there's no edges from A1 to B2 and so on. Is it clear?
Yep.
All right. So here's the theorem. We got this there was a paper by Tomon, which was also used in there's a theorem in the paper by Tomon that was also used in a paper by Park and Tomon. And that's a wonderful theorem. And we were trying to see, can we use it for anything else? But we found an improvement of it. So this is our improvement. And I want to do the proof. So we're given a graph with a bipartition. So choose a vertex in A, choose a vertex A1 in A with as many neighbors in B1 as possible. And now choose A2 with as many neighbors, with as many new neighbors as possible. I mean, A2 might be joined to these neighbors might be joined to the people in B1, but I want to choose A2 among all the other vertices, choose one with as many new neighbors as possible. And so on. You keep choosing. The next vertex is always the one with as many new neighbors as possible, not yet covered. I mean, if there weren't any of these sloping edges, if there weren't any of these backward edges, then we'd be happy. This would be a comb. Well, we still wouldn't know what size the sets are. To be the comb we want, we need the sets are big as well. And this doesn't tell us the sets are big. So there are two problems. One is we have these sloping edges stopping it being induced. And second, we don't know what size the sets are.
And it could also be that Bn is empty, right?
Yes, it could also be that Bn is empty. So just stop the process when you covered everybody in the bottom. So new vertices won't give you any new vertices on top, won't give you any more new vertices on the bottom. Stop the process then. We don't need Bn's that are empty. Let's call this a greedy half comb. Now look, these B's as they go, they get smaller because the first vertex was the vertex with most neighbors. So A2, the total number of neighbors A2 has in the bottom is at most the size of B1. And some of them might be in B1. So the number of new neighbors of A2 is certainly not bigger, and chances are it's smaller. And sets keep on getting smaller. If they've all got the same size, then there can't be any slopey edges, right? Because he's only got B1 neighbors, he's only got at most B1 neighbors altogether. And if B2 has the same size as B1, there's no extra. He can't have any more children in this direction. So if all the B's have the same size, we get a big comb, and that's great. We'd have to figure out what the numbers are, but that would be good. So what if they have almost the same size? What if I tell you the last one is at least 2/3 of the first one? So they're all approximately the same. Now here's a theorem. If we get a greedy half comb where Bn is at least 2/3 of B1, then either the union of the B's is this quantity, 3.46 times gamma times B1 to the half, or you get a T gamma over T squared cone. So if you have a half cone, where the sets are about the same size, then either the union of the B's is not very big, or you get the cone you want. And here's the proof. So suppose you don't have the kind of cone you want. Now you work through the sequence backwards. You look at a vertex. Well, let's say AN is good. I want to say a vertex is good if it's got lots of neighbors that people we've already chosen don't cover. So certainly AN is good because nobody covers these vertices in BN. Nobody except AN is adjacent to these vertices. Now, what about AN minus 1? How many vertices in BN minus 1 are adjacent to this good vertex, AN? Maybe some. Actually, it can't be more than a half. And I want to say a vertex is good if half its so a vertex AI in general is going to be kind of said is going to be good if at least half the vertices in BI are not joined to any later vertices that we've already chosen to be good. So in fact, you can say this guy is guaranteed to be good because AN can't cover more than half of these. You can check, but it doesn't.
Right? Here in this case, you cannot cover more than 1/3.
I think 1/2, because this set might be smaller than B1. It might be 2/3 of B1. Maybe it's 1.
Oh, I see. Okay.
Maybe, but so this guy's good. Not all his children are not. Some of his children might be bad children of AN, might be awkward children of AN, but a lot of them are good. At least half of them are good. They're non-adjacent to AN. Now, what about AN minus 2? Maybe nearly all of them are joined to either AN minus 1 or AN. That's possible. So maybe we can't use AN. Maybe we don't want to use this guy. So the process is we're trying to pull out a comb here using at least half of each BI. And perhaps we can't use AN minus 2 because these vertices are all covered by AN minus 1 or AN. But so then we'll try this guy. I mean, maybe there you can get half of Bn minus 3 non-adjacent to AN minus 1 and non-adjacent to AN, and so on. So you just pull out this thing greedily and see what you get. You certainly get a cone, right? The sets at the bottom are each of size half the corresponding BI, which is 2/3 of B1. So half of it is 1/3 of B1. So we're getting a cone with a sets of size 1/3 of B1. And we'd like to know the cone is big. So what can we say about how many blue stars do we get? I suppose there are T good values of I. And now, so a vertex AI has good children, has straight down children, and it has awkward children, or children off to the side. Let CI be the children off to the side of AI, the ones not in BI. Then how big can CI be? Well, we know how many children can this guy have leftwards. We know here it's got 2/3 B1, and altogether it's only got B1 at most, because B1 was the one with biggest degree. So the number of side children is only at most 1/3 of B1. Maybe that's what you said, Samuel, right? So yeah, the number of side children is only 1/3 of B1. So CI is at most 1/3 of B1. So take the union of all the, look at all the vertices in the B sets that are awkward children of anybody and call it C. So that proves C is at most T times 1/3 B1, because any one vertex on top only has B1 over 3 awkward children. So altogether you can only get that many. But on the other hand, if a vertex I is bad, or if a number I is bad, that means that half of its BI belongs to C. It's an awkward children of somebody else. It's an awkward child of somebody else. So if I is bad, then C intersect BI is at least half of BI, which is at least a third of B1. So add them all together, size of C is at least total number of bad values times B1 over 3. So now compare these two things. That tells me that T is at least N minus T. So T is at least half N. So what have we proved? So we just proved we know there's a T B1 over 3 comb. This blue thing is a T B1 over 3 comb. And we know T is half N. And we know there's no T gamma over T square comb. So B1 over 3 is less than gamma over T square, which means that you get T is this inequality tells you T is at most that, and we know N over 2 is at most T. So putting that together, that tells me N is at most 2 root 3 times gamma over B1 to the half. So the union of all the B's, it's N times B1 at most, and N times B1 is this. So multiply it all together and you get that quantity. So if all the sets are nearly the same size, then we get a good bound, just gamma times B1 to the half. And this is what we just proved. If they make a greedy half comb where Bn is at least 2/3 B1, then either the union of the B's is only that big, or you get the kind of comb you like. Now, what if I don't assume they've all got the same size? What if they're arbitrary sizes, these B's? I still want a greedy half comb, but what if they're arbitrary sizes? Then you get exactly the same thing, except the number gets bigger. Instead of 3.46, you get 19. And the reason is, well, these BIs get smaller. So keep going, read along here until you're at size 2/3 of B1. So put in a line when you get, make a cut off the ones which are at least 2/3 of B1 from the ones that are less. And now make another cut for the ones that are less than 2/3 of that. And another cut for the ones that are less than 2/3 of that, and so on. You break it into some number of intervals. But inside each interval, it's a greedy half comb satisfying that condition. So the union of, either we get the kind of comb we like, or, and assume we don't, or the union of these BIs is only 3.46 gamma times B1 to the half in here. But what about in a later interval, say here? In any interval, if I'm looking at interval number S, then the BIs are between 2/3 to the S minus 1 and 2/3 to the S times B1, because they keep getting smaller by factors of 2/3. So the union of the BIs in that interval is only 3.46 times gamma times 2/3 S to the B1. And to get the union of everything at the bottom, I just sum them. And the nice thing is, this is a geometric series. Doesn't matter how many terms you've got, it converges. Right? The later terms, the BIs of the later terms, the union of the BIs of the later terms is smaller. It gets smaller geometrically. You can add them all together. It doesn't matter how many terms there are. And if you sum this, you get, that's where the 19 comes from. So you sum this thing, and you sum 2/3 to the S square rooted over all S, and that comes to be a bit less than 19. So we now prove this thing, and I'm getting short of time. Let me keep going. That's the comb lemma. Now, that's not what we really wanted to prove. We really wanted to prove the rake lemma. Right? If you have a critical graph, for any graph H and for any T0, you can choose gamma, so that if you choose C sufficiently small and you look at a C critical graph that's H-free, then one of them contains a big rake. So how can I use the comb lemma to prove that? There's a theorem of Erdős that's good for all these induced subgraph problems, as far as I can see. It says, exclude any graph H, you give me any graph H and any epsilon, there is a delta, such that if I have a graph that's H-free, then you can pick a linear size subset of its vertices, X, subset X, the size delta times G, such that one of either G restricted to X or G complement restricted to X has got small maximum degree. It's got maximum degree only epsilon times delta times the size of G. Notice I'm talking about the degree in this subgraph. I'm not talking about the degree of the vertices in X. I'm talking about the degree in G restricted to X of the vertices in X. Right? They can have lots of neighbors outside of X. They just don't have many neighbors inside of X. That's Rödel's theorem. And so now let's prove the rake lemma. We're given an H and T0. Choose epsilon this small. And let delta satisfy Rödel's theorem. And let gamma be this quantity. And then we claim gamma satisfies the rake lemma. So let's prove it. Take C very, very, very small. And suppose you've got a graph that's H free and C critical. Now, by Rödel's theorem says one of G and G complement has this big set where the degrees are small. But I want it to be G, so let's replace G by its complement if necessary. That's why in the rake lemma, it might be G or it might be G complement. But from now on, let's assume it's G that has the big subset of small degree. And now we're going to prove that G contains a rake. And I can, just for convenience, let me assume exercise exactly delta times G. If it's bigger, just throw away some vertices. I mean, I agree delta times G might not be an integer, but it's not going to matter. And now we'll show that actually G restricted to X contains this rake. Suppose it does. Well, then the rake has got all these big sets. It's got sets of T sets of that size. So, and all these sets have to fit inside of X. So that means T times this number is at most X. And X only has size delta times G. So T has to be at least gamma over delta. And we chose gamma over delta to be 1 over 400 epsilon, which is T0, or at least T0. So if you've got a rake, then it guarantees that T is at least T0, which is one of the things we promised in the rake lemma. So we just have to prove it has a rake like this for some T at least 1. Okay, let's try. So here's my C critical graph. I get my big linear set X where the max degree inside here is only epsilon times delta times G. Now, take any subset of it, the red set, take any subset, and look at the max degree inside this subset. Let's call it delta. Choose a vertex of that max degree. Now, inside here, there's a big stable set by induction, right? I mean, this is a proper subgraph of the original graph, and the original graph was C critical. So kappa of this is at least delta to the C. But kappa is alpha times omega, alpha of this set times omega of this set. That's at least delta to the C. But omega of this set is at most omega of the whole graph. So that tells me there's a big stable set here. Alpha is at least delta to the C divided by omega of the whole graph. And I get a big stable set in here of that size. Now look at the people outside with neighbors in that stable set. How many can there be? How big can that set be? Here's where we can use the comb lemma. And if I get a comb here, in the bipedal graph between top and bottom, if I get a comb here, then that would be the rake I wanted. So we can assume this set only has size, whatever the comb lemma said, 19 times gamma times delta times G to the half. And so therefore, for any set Y, there's this stable set in it. So if you look at all the vertices that have neighbors in the stable set, there's only these, 19 times whatever, plus that vertex itself, plus another maybe delta vertices. So for any set Y, there's a set Z which is stable. It's got size at least delta over C divided by omega. And if I count it plus all its neighbors inside of Y, it's only that size. That's good. That's helpful. That's what we want. How can we use it? Well, we know something. We know Z is at least delta to the C over omega G. So that tells me delta is small. Well, if I know the size of Z, that tells me delta is small. And if delta is small, that means that this set is small. So we would like to sort of eliminate delta between them. But there's another thing we know about delta as well, that delta is at most epsilon times delta times little delta times G. I'm sorry, I've got a big delta and a little delta. It made sense when I was writing it, but I see saying it out loud, it's not so helpful. But anyway, we're all inside of X, and the max degree inside of X is only epsilon times delta times little delta times G. So we know two things about delta. One is it's only that, and it's at most that. So let's define f of k to be that quantity. Yeah, that's right. This quantity where delta is defined to be the min of those two things. There's just some complicated function. Then what we proved is for every set y inside of x, there's a stable set z inside of y, such that if I look at y and all the people in z with, if I look at z plus all the vertices in y with neighbors in z, you only get f of z of them. So again, here's my set x. For any set y, there is a set z, so that if I look at all the people with neighbors in z plus z itself, it's only f of z. All right, getting there. So let's apply that for a value of y. Let's apply it for y equal to z. We get a stable set z1, and it's not got very many neighbors. Now let's apply it for this set. We get another stable set z2, and it's not got very many neighbors. And notice there's no edges between z1 and z2, because this set contained all the neighbors of z1 that were in the set called y at that stage, which was at that stage was the whole blue bag. And now we can do it again. We get a z3, and there's no edges between z1, z2, z3, and so on. So the union of all these z's is at most the stability number of the whole graph, which is less than g to the c over omega. On the other hand, the sum of the f's is at least, it includes all of x, because we keep on going until we've used up all of x. So the sum of the f's is at least the size of x, which is at least delta times g. And now you go back and try to remember what that function f was. And now you do some optimization. If I keep this quantity fixed, how do I maximize that? What's the largest this can be? And you figure it out. And it turns out this is a contradiction. I'm not going to do the rest of that argument, but this turns out to be a contradiction. Anyway, so that's the... so that turns out to be a contradiction. That proves the rake lemma. So let me show you some other applications of it. Here's a theorem that I mentioned at the start. If you take any forest and you look at the star expansions of, you take the star expansion of H, the star expansion of its complement, and their complements, that has the Erdős-Hajnal property. Let's see why that's true. Now, there was the theorem I mentioned earlier, that if you exclude a forest, if you take a forest, there is an epsilon. I mean, okay, let me explain where I'm going. Back here, we did all this work to get a rake. And then all we did was said, well, there has to be an edge between two red sets. And that gave us C5. But can we get something more interesting than just an edge? I mean, how about you can get a 3-vertex path, for instance, if you wanted. We proved that in a separate theorem, but it turned out to be, it disappeared again, but it's true you can get a 3-vertex path. But can we get better things? Can we get more exciting subgraphs in the red graph? And that's what I want to talk about here. So we proved that if you exclude a forest and its complement, you get a linear size pure pair. But here's something better. We proved it in the same paper that if you take, for any forest, there's a number d, so that if you take d pairwise disjoint subsets, then either there's a, either you get a rainbow, let me turn my phone off. Either you get a rainbow copy Rainbow means one vertex in each set. I mean, at most one vertex in each set. You know, vertex in one red set, vertex in a different red set, vertex in a third red set. It's all spread out. So you either get a rainbow copy of one of H and H complement, or you get a pure pair of size at least the smallest of these B's divided by D, but still linear. Well, I mean, if the sets BI are linear. So that's stronger than this, but we happen to prove it in the same paper. So it's very convenient for us that we did prove it, because now we need this stronger form, the rainbow form of it. Because that's what we've got, right? We got a lot of disjoint sets, and what we would like to get a tree, one vertex in each set. Let's go back and look at a rake. If I can get a tree, you know, say I can get a 4-vertex path, one vertex, oh dear. One vertex here, one vertex there, one vertex there, and one vertex there. If I can get a 4-vertex path, that would give me the star expansion of a 4-vertex path as an induced subgraph. Any rainbow subgraph I can get here, we have its star expansion in the whole graph. So any rainbow subgraph you can produce, you're happy with. And so this rainbow theorem about trees, about forests, says basically you can get a rainbow copy of one of H and H complement, or you get this pure pair of size at least the smallest of these guys divided by D, which is only a constant. I'm cheating a little bit because we can't get a pure pair which is linear. But this isn't linear, right? The B1 is not linear. It's only the comb size, the size of the bags at the end of the whatever it's called, the rake. And we don't really know that's linear in the size of the graph. But it doesn't matter, it turns out. We can work on this, and I don't have time to explain, but this theorem is good for giving you rainbow copies of forests, and it's good enough to prove this for us. And I think I won't do any more details of that. So here's a consequence. Suppose I'm happy to exclude the complement of a forest. Then suppose I'm happy to exclude complement of H and not its star expansion, just H itself. Then I don't have to exclude all 4 of these graphs, because you know the H2 contains the complement of H, and H1 bar contains the complement of H. So I don't have to exclude those 2. If I exclude the complement of H, then it's enough to exclude the star expansion of H and H2 bar, whatever that is, the complement of the star expansion of H bar. Well, all right. You can do better than that. You can prove for any forest, all I have to exclude is the complement of the forest and the star expansion of the forest. You don't need to exclude H2 bar. And the proof for that is, well, it's not quite a consequence of that rake lemma, because in the proof of the rake lemma, there were 2 cases. You had a linear subset, maybe a small degree, or maybe a small degree in the complement. And if it was small degree in the complement, you move to the complement. I don't want to do that step anymore. I want to have a separate argument if you've got small degree in the complement. Because this, our old theorem about forests, we had another strengthening of it, that for any forest there's an epsilon, such that if you just exclude the forest and you go maximum degree at most epsilon G, then there's an anti-complete pair. All that matters is a pure pair, but in fact you get an anti-complete pair of linear size. Now here we don't have to exclude the forest complement, but we do need to say that the max degree is less than epsilon times G. But that's nice, because in our case now where we've got a graph where we're excluding the complement of forest, and we're worried about the case when we get a linear set where the degrees are huge. That means in the complement graph, you've got a linear subset where the degrees are small and you're excluding the forest. Exactly these hypotheses. So that means you get a linear pure pair, and you can't get a linear pure pair. So that case just goes away. I've done my full hour. Okay, I guess I'd better stop.
No, you can take some more time. Yeah.
Like I've only got one more thing to do. How to do C5 with a hat to prove So this is C5 of the hat, and this is its complement. Let's prove that C5 and its complement has the Erdős-Hajnal property. This hat notation is not so great, right? If you may put a hat and put a bar, you're getting a bit silly, but for now anyway. Let's see how to prove that. So what can we do? You choose gamma and C, making the numbers work. And I'm not going to go into the details of that. And now suppose I've got a C critical graph, which is C5 hat and C5 hat complement free. And now we can replace G by its complement if we have to. So we get a rake. And what do we know about this rake? Break each of these red sets into components. So for each red set, look at the subgraph induced on it. It might not be connected. So partition it into components. Now, no vertex in a red set is joined to one end of an edge and not joined to the other end of an edge in a different red set. Right? If a vertex is joined to one end and not the other, then here I've got a C5 for the hat. Right?
Yeah.
And also what does that tell me? That tells me that any two blue sets are either complete or anti-complete. Because look at any two blue sets. If it's two blue sets coming from the same red set, they're anti-complete because they're both components of this thing. If the blue sets, say this blue set and that blue set coming from different red sets, well, suppose this was not complete to that and was not anti-complete, then you can get a vertex in one of them with a neighbor and a non-neighbor in the other. I mean, if every vertex here was either complete or anti-complete to that, you'd have one of each, or else you. And then every vertex here is mixed on that set. So I can find a vertex here, say, which has a neighbor and a non-neighbor in this blue set. But this blue set's connected. So if you look at the set of neighbors of my vertex and the set of non-neighbors of my vertex, there's got to be an edge between those two sets. And that's what we said can't happen. You can't have a vertex, where did it go? You can't have a vertex like this, a vertex joined to one end of an edge and not the other. So every two blue sets are either complete or anti-complete. Now, another thing we know is you can't get a red rainbow triangle, because if you did, this would be C5 for the hat again. So that means, you can't get a rainbow blue triangle, because, if I look at again, let me go back to my blue set. If I had a blue triangle, a triangle all with its vertices all in different blue sets, no two of them could come for the same red set because there's no edge there. So any triangle that's rainbow with respect to blue is also rainbow with respect to red, and you can't have that. So why is that a good thing? Well, we've got all these blue sets, and every two of them are complete or anti-complete. So, there's a pattern that they're joined in. Replace each blue set by a vertex. And if two blue sets were complete, put an edge between the corresponding vertices. Now that triangle, that graph we just made is triangle free. And we know lots of stuff about triangle free graphs. For instance, they've got a big stable set. They've got a stable set of size alpha, number of vertices to the half, or almost. So if all the blue sets were the same size, I'd take my stable set of blue sets of size square root the number of blue sets, and that would contradict the party lemma. But the problem is they're different sizes. But there are results for triangle-free graphs where you put weights on the vertices. If I have a triangle-free graph and I put weights on the vertices, and I want to get a stable set with a weight in it is big, you can do that still. There are theorems about that. I'm not going to go into the details here. But what you do is for each blue set, you put a weight on it, which is kappa of the subgraph induced on here. And those weights work nicely and it all comes up. And so you get a contradiction to the party lemma anyway. All right, let me stop there. Thanks very much.
Okay, thank you very much, Paul.